I'm going to be navigating Slifer and introducing some of its features for you. I'll just go to the MATLAB command line and type Slifer. Up it comes with a default scene. That default is set up for 21 coefficients, and it's going to be a linear phase filter. We can observe that filter in the time domain by looking at this narrow plot here. This is the impulse response, and since it's FIR, this coincides directly with the coefficients of the filter. This large window here is showing me the frequency domain, and in fact it's plotting something called magnitude. You'll need to read in the help file associated with this tool exactly what our definitions of that are, but this is the phase free or amplitude, the various names in the literature for this. Now when I mentioned the help file, always you can go up under here under help and learn about the different layout features of the tool itself. You can go and see screenshots and see what's available in terms of the various controls. You can also, if you have a question about a particular control, you can do what's this and click something, and eventually up comes the window which then shows, I think it's gone behind here, it then shows that particular area in the help file and you can read about it. More importantly, probably for most users, will be go to some examples of designs which you can do with this tool, and this is then probably the most important help file available. You go in here and there are a bunch of, well, it seems to be about maybe almost a whole alphabet's worth here of designs which can be clicked on, and then we see screenshots, all the maneuvers of some particular example taken from referenceable in the literature so that you can compare our results with what has been published in other papers. So you do have a link to the outside world. You have lots of help if you want to plow through it. Let me just show you some more things about this. As well as this time domain plot, frequency domain plot, you have other plots, some of which are frequency domain plots. This is showing an error, but we can go through this list of different things and look at, for example, dB plots and so on. This is our what we call our cameo plot. It has tons of things which you can look at. Now, of course, this is on quite a small scale, and you might wish to toggle it into better visibility. You can do this by clicking on the vertical line here, and this then swaps position with what was previously in the narrow axis. And you can even go further than that by exporting this information out to for external plots. The final picture we have is the PoleZero plot. Now this is live. You can actually move these zeros around, although we don't claim that for this tool that this is a very precise way to do any design of a filter, but it does show how everything interacts with everything else in the time domain, frequency domain, and the Z domain. Let me go back to the low pass filter. I can always reset that filter here. In fact, I can choose up in the upper right hand corner. There are lots of things about filters. I could choose other standard things, for example a bandpass filter, and I could grab the band edge and move these little dots here, and what I'm doing is I'm moving and reshaping this red line. Now this is my target profile, and my filter is trying to design to that. And you notice these little round circles, these we call pearls. These are located in terms of frequency at equispaced points in the traditional frequency sampling manner. Very powerful design technique which has been around from the earliest days of DSP. Now these little tiny squares show the frequency locations corresponding to those pearls, and at the moment, since we have 21 coefficients, I look up in the right hand corner, this spacing is 1 over 21, because that at the moment is normalized frequency seen going all the way around the unit circle, and therefore having 21 of these little pearls that can be moved. I can put a grid on here and you can see vertically the alignment, and you can see that as I change this I'm getting a new design each time. I'm going through an inverse DFT operation to go from the magnitude, so-called here, Some authors will call it amplitude, some will call it phase-free or zero-phase design. And this is described in the help file. And we're going up here and getting, of course, a different impulse response each time and different PoleZero pattern and so forth. So when you use a tool like this, you either start off having a particular standard type of design, of which we have quite a number, including differentiators, Nyquist filters, again can be read about in the help file. And we're not restricted just, however, to things which have been provided as standards. We can actually create these in another way. One way we can do is to go up to the upper region of this GUI, and we have something called the profile calculator. This will launch a subsidiary window which we can make use of. You notice it's taken that bandpass filter I had and it's put this in all of these four windows. I can operate on this. For example, I could circular convolve A with itself and put that onto B, and you notice a different sort of shape. Now the way this can be useful, and I can do other sorts of calculations here, but I can send this back into Slifer and get myself some sort of exotic shape by a combination of these calculator sort of buttons. I could of course square that perhaps. I'll square, well, it says square A. I don't want to do that. I want to square B, because that's the one I just created. So I just overtype that, and I actually applied that operation to trace B. Now I'm ready to ship it back, let's say, to Slifer. This might have some meaning to me. I'll send this to Slifer by clicking on that and also directing it to the particular one I want to send, and it's come back into Slifer. And you notice that my 21 coefficients have done a pretty good job of meeting this, because the yellow curve is right on top of the white curve. So you can always, of course, subtract these and find out what the error is, and by going over into here and perhaps looking at absolute magnitude of error, you might bring it in this way, and you might see then as we move the pearls in the vertical direction what's happening to the arrows. We're not constrained, however, to just this traditional frequency sampling method. We can break this off by going to the target mode, and we can deploy these little pearls quite close together. Of course, this opens up the possibility for arrows to break off elsewhere, but basically this is helping us to handcraft a filter, so that if we come in with something which is close but needs some nudging, we can bring it in, or of course we can do a lot of the design ourselves from the start point. We'd like to be able to break off the red line, so we can do that as well. Go into setup again and go to freedom mode. Now we can go to any altitude and any frequency, being careful not to get the two pearls too close together, because we will then have a poorly conditioned Vandermonde matrix involved. Well, there are two other types of design that can be done, although this is fundamentally a frequency sampling, either of the type 1 or type 2 design type that you can read about in papers like in books like Rabiner and Gold. There's a slightly different situation. I would set it to this arbitrary filter, and I see a different sort of error come up on the top trace. Set everything up here, and you see that indeed it does make some difference. But you go much further than that by being able to have the total freedom of how you move these pearls. Underneath here we see ways to export our results, because after all it's the coefficients that we're after. As a result of all this, we can export those to Workspace, various tools, even to Simulink. We can change the question of whether or not we have a linear phase or a nonlinear phase filter. If I bring this in here and perhaps go to something more familiar like a low pass filter, so we maybe even have a few more coefficients. Let's have 41 coefficients. I'm changing this up here. Now as I move these, I also get this supplementary way of designing things by nudging a bit in the time domain, but of course they are at the moment going in in pairs because I do have the linear phase relationship going. Now, whenever I want to measure anything, you notice I've inadvertently clicked on that. I've got a measurement here, and I can kill that. I can put these measurement boxes on here and run them along. It's quite handy to be able to measure things. I can measure them that way, and I have other sorts of features like that, which we can see by making use of these various menu items up here, which you can read about in the help file. Okay, so we can change filters in various ways. We can output them. We can make use of that profile calculator. I was just about to say what happens if we want to disconnect the relationship between these. And here I'm now moving this sample all by itself in the time domain, and there's no corresponding movement back here. But that should of course be resulting in phase nonlinearity, so I can have a look at phase, say in degrees here. Probably it will be better to look at group delay, but anyway, we'll do it this way. And we see this as we move it. You can see some very nonlinear things happening over in this cameo plot. So that's phase nonlinearity. You notice that that also means that as I move this, I no longer have a quartet of zeros. I've broken the ones inside the unit circle because of this non-insistence on linear phase. I can do one more thing. I can have complete freedom between upper and lower zeros here, because this conjugate cousin at the moment is moving with this, and this is because I've got an insistence initially on real filters. But I can go up and allow complex filters to happen, and now this will be a free agent. And so of course I don't have to have symmetry, and therefore I really need to look between minus Nyquist and plus Nyquist. I'm a bit bored by all this dense grid. I'll get that off and go to that type of grid right there, visibly a little bit better, and I'm moving this quite independent of the negative frequency ones. The price of that, however, is I've picked up another picture up here, which is the imaginary component of the impulse response, and that's available to me to move, of course, as before, and I can jiggle these without having much luck. There, I've got it right on it, and so I can move the real part independent of the imaginary, and I can of course strip away that and force that filter to go real, and that in the future it's better to click back to this so that I'm forced back totally into the real situation. I can invoke another tool which comes up called CPIG. This is sort of nice because it comes up on top and shows me now my impulse response. It shows me my PoleZero pattern and allows me to track down a lot of the things about it independently of our cameo plot. This might be the kind of thing that we would want to archive and put into a document somewhere to describe the goodness of our filter. If I go back to low pass filter in a clean situation, got my 41 coefficients, I can seriously measure the goodness of that filter by going to view quality measure. This comes up and draws me a template either linearly or in dB, and shows me what my stop band ripple level is, which is measured here, shows me the transition parameters here between pass band and stop band, and then shows me quite a lot of information about the pass band itself. So this again is good for archiving the final result or of goodness of this filter. There's an enormous number of operations here which we can do to coefficients and see the corresponding frequency domain effects. These are basically echoes of what you'll find in lots of textbooks about the discrete-time Fourier transform, flipping in the time domain, what this does in the frequency domain. But at the very bottom of this, we open up two other kinds of design. We can either optimize by least squares. This is sometimes called impulse invariant. You notice there's a slightly different filter has come out now. I can look at this maybe in dB. It might be better. I can bring this up here, take off the automatic scaling, come down to about minus 60 dB, and I can probably see the difference between what I just did and this one. You notice a bit of a side lobe difference. I go back into that least squares and you see that there is a difference in that design. More dramatically probably is equiripple. This is a famous Parks-McClellan operation, and we're seeing now with unweighted facilities how the side lobes are looking here. So we do have a couple of subsidiary ways of designing, and of course once we bring those in, they become controllable for further fine-tuning by means of frequency sampling techniques. We have lots of cosmetics we can do, things to change the color of the plots and to export them, import them, and also the axes can be zoomed in on. If, for example, if I want to get right here between any two limits in terms of frequency or time, I can do that. So this tool is, in summary, a very powerful handcrafting tool which allows you to design real or complex FIR filters, and to also then to document those and save those results, archive them, and so forth. To get more proficient with this tool, you simply have to play with it a little bit, and when you're stuck, have a look at the help file.